Okay, just more practice here in example 2 of using basic identities to simplify the expression. And so here in letter A, I have tangent x times cosine x. I know that tangent x is sine x divided by cosine x, and that's going to be multiplied by cosine x. And so therefore, what do I notice? That cosine x will cancel out, and we will just be left with the sine of x. Now, sometimes you're going to change things and nothing's going to happen, or you're going to run into a brick wall. That is why we have erasers, is to scratch out or erase and try something different. But something should be happening on these problems. You should see things simplifying, reducing, canceling out, becoming nicer as you work through the problem and use identities to try and simplify. Okay, here in letter B, what I notice in the numerator is that I have a Pythagorean identity. That second Pythagorean identity tells me that 1 plus tangent squared x is equal to secant squared x divided by cosecant squared x, which was already in the problem. Now, I can rewrite this in terms of sine and cosine to see if maybe I can get something better. And so secant squared I know is 1 over cosine squared, and cosecant squared I know is 1 over sine squared x. And so what does dividing by a fraction really mean? It means to keep the numerator the same and change to multiplication and multiply by the reciprocal of the denominator, which would be sine squared x divided by 1. Now, multiplying across is going to give me sine squared x divided by cosine squared x, and I'd notice that that is just the squared version of one of my quotient identities. And so sine squared x divided by cosine squared x is going to equal to tangent squared of x. Okay, here on letter C, I don't immediately see any basic identities that I could use to try to simplify this expression. But what I do notice is that I have two terms separated by a minus sign that each have 1 cosine x in them. And so what I'm going to do here is factor out a cosine of x. And so what that's going to leave me with is a 1 minus a cosine squared x. And so now this goes back to what I discussed on the very first slide of the notes, which was that you need to be able to recognize Pythagorean identities in different formats. And so what I mean by that is that we know as a given fact that sine squared x plus cosine squared x is equal to 1. But if I solve this for sine squared x, it means that I'm going to subtract over cosine squared x. And so that's going to become sine squared x equals to 1 minus cosine squared x. And so now you notice that that right there matches my parentheses. And so be good at recognizing immediately whenever you have a rearranged Pythagorean identity. And so this is going to become cosine x multiplied by sine squared x. And from there, there's not really any other basic identities that I could use to simplify this. And so therefore, I'm going to call that my final answer. Okay, we actually did this exact same problem back in example 1. But I want to show you that there's actually a different way to do it that you could actually end up with the exact same answer. And that's going to be the case a lot of the times. There's not necessarily just one right way to get to the most simplified form. And sometimes we're not always going to necessarily agree on what the most simplified version is. And so that's why it's very important when you're doing trig identities to be very clear in your work so that it can be followed. And so what we're going to do here, instead of using the Pythagorean identity that we did when we did this problem earlier, is we're actually going to distribute this cotangent squared x into the parentheses. And so cotangent squared x times 1 is going to give me cotangent squared x, and then plus cotangent squared x times tangent squared x. And what I notice now is that in this second term, I am multiplying cotangent squared x by its reciprocal. And so from our previous discussion, anytime I multiply something by its reciprocal, the result is going to be 1. And so this is going to be cotangent squared x plus 1. And now what I notice is that my third Pythagorean identity has come into play. I have cotangent squared x plus 1, and I know that that's equal to, by a Pythagorean identity, cosecant squared x. And so some of you are going to see right off the bat, 1 plus tangent squared x is equal to secant squared x, and you're going to work it like we did in example 1. And some of you guys are not going to see that right off the bat, and so you might start to distribute the cotangent squared x. We all get to the same place as long as we follow the rules of trig identities and the rules of algebra. Okay, here on letter E, we're actually going to do this one two different ways so that we can get two equivalent expressions for cosine squared x minus sine squared x. And I want to caution you just right now that this is not equal to -1 based on some false Pythagorean identity. So just because there's a negative in the middle of cosine squared and sine squared, that doesn't mean that you could change it to -1. So for example, let me show you what you could do based on the identity that we know. We know that sine squared x plus cosine squared x is equal to 1. So therefore, what you could say is you could say that negative sine squared x minus cosine squared x is equal to -1. That would be a legit identity, because what you did is you took the known Pythagorean identity and just multiplied the entire identity by -1. This, however, is not going to equal to -1 because the cosine squared x is not negative. And so now that we've got that out of the way, we can continue to work this problem. Now we are going to use a version of this Pythagorean identity, and so I'm going to erase this part and just look at this Pythagorean identity. What do I know? I know that sine squared x is equal to 1 minus cosine squared x. And so what I can do is I can replace sine squared x in this identity with 1 minus cosine squared x. And so that will say then cosine squared x minus parentheses 1 minus cosine squared x. Distributing that negative is going to give cosine squared x minus 1 plus cosine squared x, and then collecting the like terms will give me 2 cosine squared x minus 1. And so that statement is equivalent to the given statement cosine squared x minus sine squared x. But we could also do this another way, where we replace the cosine squared x with 1 minus sine squared x. So because, for example, this right here is really the same thing as cosine squared x is equal to 1 minus sine squared x. And so if we did that, starting from this given identity, we could say that this is 1 minus sine squared x. That would be replacing the cosine squared x, and then minus another sine squared x. And then collecting the like terms, we could have 1 minus 2 sine squared of x. And so the two boxed expressions along with the given expression are all equivalent, and which one you end up with really just depends on a lot of things. It depends on what you want to end up with. Maybe I want something that's only in terms of cosine. In that case, I would go with this expression. Maybe I wanted something that was only in terms of sine of x. Therefore, I would go with this expression. If I wanted both of sine and cosine to be in there, then I would go with this expression. They all mean exactly the same thing. They just have slightly different formats or names, but they are all equivalent expressions.